In this video I'm going to go through Task 1, Unit 1 EDEXCEL Physics Mechanics for the ISP. The things I want to focus on are the differences between scalars and vectors, a list of base units and the information that can be deduced from displacement, velocity and acceleration time graphs. These two things, make sure you got it listed from the books. They're not really the textbook from these pages over here. They're pretty straightforward. Okay, so remember, scalars have just magnitude, vectors have magnitude and direction, as many of us know from Despicable Me. And there's also a list of base units as well that you need. There's only 3 of them that are really used in Unit 1. That's kilograms for mass, that's meters for length, and that's seconds for time. Okay, so and also there's information that can be deduced from displacement time, velocity time, and acceleration time graphs. Just get stuck into our explaining everything tasks, which help us to sort of frame our thoughts. So, what can we conclude from the shape of distance time and velocity time graphs? That should be from the shape of a distance time graph and a velocity time graph. Okay, yeah. So right, if we have a distance time graph, okay, so if I had a graph of distance or displacement against time, okay, and if I had a graph of velocity against time, they can tell us different things. So a lot of us know much about these from GCSE. So I'll just draw the same shape on both of these and we'll talk about the shapes that we have. Okay, so in a displacement time graph, this bit over here, that's going at a constant speed. Over here, it's stationary, it's not moving, the distance is changing, and over here it's going at a constant speed again, but faster than before. In the velocity time graph, we've got an idea of constant acceleration at the start, then you've got constant speed and a constant acceleration again, but greater than before. If you had a displacement time graph and it curved like this, what that would mean is that acceleration is taking place. Okay, if it curved the other way for a displacement time graph, that's deceleration. Okay, and then over here, obviously, it's going at a constant. It's stopped. It's got stationary, or it's at rest. Final thing I just want to talk about quickly is if you've got a displacement time graph and there's a line on it like this that goes back, that goes down, that means it's going backwards. And a similar sort of idea on a velocity time graph. Okay, so if you've got a line like this, okay, well, this isn't going backwards yet, it's just decelerating. But as soon as it ends up getting a negative velocity, so it's underneath the x-axis, that means it's going backwards. So what key information can we figure out from these graphs? Well, we've got 2 things we can really look for: the area under and the gradient. So in a displacement time graph, the gradient, so change in y divided by change in x, so how much your y value has changed divided by how much your x value has changed, okay, that gives you the velocity. So the gradient of a displacement time graph gives you velocity. The gradient of a velocity time graph, the same idea, change in y over change in x, okay, gives you the acceleration. But also the area under gives you a bit of information too. The area under this gives you the distance travelled. So you can see this is made up of different objects. Okay, you've got 4 objects. You've got a triangle there, you've got a rectangle, you've got another rectangle, and you've got another triangle. So you've got 4 objects there, and they allow you to figure out the area under the graph and therefore the distance travelled. The only other thing to really mention is if you have a curve like this and you want to figure out the speed at a specific point, say over here, you'd need to draw a tangent on the line there. So if you want to figure out the speed over here, you need to figure out the tangent. So you draw a line like that. Okay, it's at the gradient of the tangent, and that is the velocity at that point. If you just took the displacement off this side and the time off this side and divided one by the other, that's only going to tell you the average velocity. Okay, if you did a tangent and took the gradient of tangent, that would tell you the velocity. Okay, and a similar idea for acceleration if you had a curve on a velocity time graph, but they don't come up particularly often. Okay, so that's covered all the key words and covered both types of graphs as well. Explain how you can use strobe photography or video analysis software to analyse the motion of moving objects. So let's quickly go onto the internet and have a look. Okay, so if I just type in strobe photography, there's a really good one of a golf club, if I remember correctly, which I also use in lessons. So let's get this picture up. This one over here is very good. See if we can view this image and make it bigger. Oh, there we go. Brilliant. Okay, so you can see the club at different. Oops, you can see the club at different times. Okay, so the time between each of these photos is the same. The distance, well, if we had a scale, so if we knew how long the golf club was, okay, you could figure out how quickly it's moving, because you could use that to figure out a scale. So here's the golf club. You can use that to figure out the scale in terms of length and in terms of with a ruler, and the length of what that is in real life. So compare those two and have a reference point, say like the end of the golf club. Then you can see how far it's moved between each shot. Well, if each shot, what I mean by shot is not a golf shot, but a shot as in a shot in the camera, so each picture in the camera. So if between each picture in the camera it was 0.1 of a second, and between here and here we measured it and moved say half a meter, so your distance will be 0.5 and the time will be 0.1, so you can figure out how fast it's moving by doing distance over time. Okay, so 0.5 and 0.1, which gives you 5 meters per second. Okay, over here you can see the distance is smaller, but the time is still the same. The time between each picture isn't changing, so you can see over here it must be travelling slower. Okay, so that's how we can use the idea of strobe photography to come up with the idea of to sort of analyse the motion of moving objects. So we can do the same thing with video analysis software. So you play the video and you pause it, you move it forward frame by frame, and that allows you to analyse the motion in terms of what's going on. Excellent. So that's the explaining everything task's done. Let's get stuck into the questions. So here we go. Question 1. So we've got a graph over here of a motorbike in the final 10 seconds of a race. Okay, it's a velocity time graph. Okay, so you've got to remember ideas about velocity time graphs. Describe the motion shown by the graph. Well, you can see it's accelerating to begin with, and then it goes at a constant speed. Okay, accelerating, and then it goes at a constant speed. Show that during the final 10 seconds, the motorbike travels a distance of 800 meters. Okay, so if you want to get distance from this graph, it's the area under. So you split this into the triangle over here with a square underneath it, and then you have the big rectangle over here. So let's do this big rectangle first. So that's 4 to 10, so that's an area, so that's a distance of 6 that direction. So 6 times by 90. Okay, so 6 times by 90 is going to be 540. Just double check that. 6 times by 90. Pretty sure I done that right. Yeah, 540. Okay, then we've got a square down over here, which will go up to 4 wide and 30. So 450 and 120 for that. So that's from the 6 times by 90, the big rectangle. Then we've got the idea of 4 times by 30. 4 times by 30, which gives us 120. Okay, so I've done this chunk. Oops, easy, don't remove this. We've got this chunk over here. We've got this big chunk over here. Then we've got the triangle over here. So remember that's half base times height. So it's half 4 times 60. So half of 4 is 2. And then we get times 2 by 60, so that's another 120. Alright, let's check I've got these numbers right. So from there to there, 60. From there to there, it's 4. It's just going to be 6 from there to there, 6 times 1, yeah. That is 430, yeah. Looks like I've got these right, but I seem to be missing a bit of a distance here. Let's see which bit I've missed off. Oops, I see it went too far. Oh, by the way, when you're describing motion, as I failed to mention, you've got to sort of say the values. So you can figure the values out, so you should be able to actually state them. So 240 and 500, yeah, so we've got that. So there we go, 780, so exactly what I've got there. So saying it's about 800, so 780 is fine, so I didn't miss any out, that's okay. Let's get back to the question. So yeah, the bit that I failed to mention for the first part of it was, if you can figure out what the value of this is, you should use that in your description. So describing the motion, so it accelerates from 30 meters per second to 90 meters per second in 4 seconds, okay, and then travels at a constant velocity of 90 meters per second for the final 6 seconds. This for the description is the way you could do it. You can figure out that acceleration as 15 meters per second squared and then state that as well if you want to, but you don't need to. But you should really. Okay, so using the axes below, sketch a graph show the distance of the motorbike from the finish line varies during the final 10 seconds of the race. So you know that over here it finishes at 780. Okay, so you can put a plot over here. Okay, and you know also that for the last chunk over here, it's going at a constant speed, so that's going to be a straight line. But how much of a distance is this? Well, we need to work our way to this. So, how much distance does it travel in the first 4 seconds? We've got the idea of 120 here and 120 here. So by 4 seconds, it's at 240. So at 4 seconds, we need to be at 240. Okay. After that, it's going at a constant speed, so it's going to be a straight line up to there. Okay, but it accelerates to that point. There's an acceleration up to that point, so it will curve to that point, and then be a straight line afterwards. Okay, so let's just confirm B. Okay, so it's the distance from the finish line, so it's going backwards. Okay, so it starts at about 780. Shows the distance from the finish line decreasing with time, so it curves the other way around. Okay, so curve with increasing negative gradient followed by a straight line. Okay, so straight line at the end, but curve with an increasing negative gradient, so it should be getting steeper and steeper and steeper. So it should be going the other way around. Let me just bring that up again. Okay, so it says distance from the finish line, so 780 away to begin with. Okay, so it should be a curve with an increasing negative gradient, and then when we're 540 away, so over here, it's at 4 seconds, 540 over here, it's going to be a straight line all the way down to there. So it curves with an increasing gradient, and then goes straight down like that. So it should be like this until 540 at 4, and then a straight line down. It's going to be like this, with that point over there being 540. And that point there being 4. Okay, so that point there is 540 and 4. Okay, question 2. It's a lovely question. This is one that I remember giving a lot of students in class, and I remember being asked this as a student, a question like this. It's a really, really clever question. So this is definitely one that I draw out on the side of the paper, so like over here or over here, as you go through it so you can see what's going on. So you've got a hot air balloon rising vertically at 10 meters per second. It's released. The graph shows that the velocity of the object varies with time from when it leaves the balloon to when it reaches ground 4 seconds later. Assume that the air resistance is negligible. So use the graph to show that the object continues to rise a further 4 meters after its release. So what's happening is you've got this balloon. Okay, it's being released. It's still going up to begin with, but it's slowing down. So over time, it slows down. There we go. And after a second, you can see it actually is still. So it will stop. And then it will start to fall. Okay? And that's what's happening over here. Negative velocity, so it must be falling. So it says, once it's released, once it's released, it's gone a further 5 meters. So that's come from this area over here. So in 1 second, it's gone from 10 meters per second to 0 meters per second. So that's how much it's risen. This bit over here, this area of this triangle, okay, is how far it's fallen. Okay, so you can see it's risen further 5 meters because that's 1. So that's the area under here. So it's 1 times by 10, so it's 10 divided by 2 because the area of a triangle, so it ends up being 5. Determine the total distance travelled by the object from when it's released to when it touches the ground. Well, it's gone a further 5, it's a distance, not displacement, it's the overall distance. It's gone 5 meters up. Well, how much has it gone down? Well, it's gone 4 meters. So if I just sketch this graph, you can see what I'm trying to figure out here. That's how far it goes up. This bit over here is how far it goes down. So that's up. That area there is down. So the distance is going to be how far it goes up added to how far it goes down. So it's 5 meters in this direction. We know that from the first question. How much is going to be over here? Well, so 1 to 4 seconds is 3, okay? And we're going from 0 to minus 30, so that's going to be 30. So 30 times by 3 and then halved. Okay, so it's 30 there, times by 3 and then halved. So 30 times by 3 is 90, halved is 45. So that's 45 meters and that's 5 meters. So overall, the distance travelled is 5 and 45. So it goes 5 meters up and 45 meters down. Okay, so 5 meters up and 45 meters down. So the distance travelled is 50 meters. Oops, just got a bit too far there. Let's get back to the question. Yep, distance travelled, 45 at 5, 50 meters. Hence determine the object's final displacement from its point of release. So how far has it actually been displaced from the point of release? Well, if that's 5 meters, it went up, and it went 45 meters down, it's going to be displaced 40 meters from its original point. So displacement is 45 minus 5, which is therefore 40 meters. Using the axis below, draw a graph showing how the acceleration of the object change from the time it leaves the balloon to when it hits the ground. Mark any significant values on the graph. Well, from the second it's released, the only force acting on it is gravity, so it's going to be minus 9.81 the entire time across, okay, until it hits the ground. So if it hits the ground at 4 seconds, that's where you stop. So a line across and label it minus 9.81 over here. So a line directly across, labelled minus 9.1 on the side. Okay, 3a, state the difference between distance and displacement. Distance just has magnitude, displacement also includes direction. So distance is a scalar, displacement is a vector, distance is magnitude, or displacement has magnitude and direction. Okay, so we've got displacement time graph for a train along a track. Okay, so you can see over this, in this situation over here, it's got a positive velocity. In this situation over here, it's got a negative velocity. So over here, it's going forward. Over here, it's going backwards. Describe the position of train A at the end of the 8 minutes covered by the graph. Describe the position of train A of the train relative to A, sorry, at the end of the 8 minutes covered by the graph. Okay. So it says over here that an idealized displacement time graph for a journey of a train along a straight horizontal track from the moment it passes point A on the track. So here's point A. The train goes away from it, and then it comes back past it. Okay, because we're saying point A is 0. So describe the position of the train relative to the end 8 minutes to the end of the 8 minutes covered by the graph. So if it originally went in the easterly direction, now it's going in the westerly direction as it comes down. So it's 300 meters west. 300 meters west. Okay, so 2 marks, one for the magnitude, one for the direction. Use the grid, figure 2, to plot a velocity time graph to show the journey in figure 1. Do the calculations that are required on the lines below the grid. Okay, so we want the velocity, positive velocity, and we want the negative velocity. Okay, essentially that's all we want. Then we need to put the scale on to do that. So the positive velocity is going to be the gradient in this direction, and the negative velocity is going to be the gradient in this direction. So positive velocity is going to be change in y, 600, divided by change in x. So that's 4 minutes. So technically we get into seconds. Oops. Yeah, they want it in meters per second. Okay, so we need to get 4 times by 60 to get into seconds. So the positive velocity is 600 over 4 times 60. Let's do our negative velocity. So we've got a change in y that's negative this time. So that's 600, and then we've got another 300 there. So that's minus 900. Okay, split those two so you can see those two separately. Minus 900 over, how long did that take? That took 4 minutes as well, so that's 4 times by 60. Okay, so the first one is 600 divided by 4 times by 60. That's 2.5. Let's change that for 900 and just add the minus in afterwards. That's minus 3.75. Okay, so we know originally it's going at 2.5 meters per second. We know afterwards it's going at minus 3.75 meters per second. So let's add that to the graph. So for the first 4 minutes, it's going to go at 2.5 meters per second. So you add a scale on 2.5, and there's that instantaneous change to minus 3.75. So all the calculations should be done down here, and they should draw in line. So it's like a zig. So it's like a Z, but with a line straight down like so. Apologies for the squeaky chair if it's making noises over me. So, a cyclist and a car are both stationary at traffic lights. They're alongside each other with their front wheels in line. Okay, the light changes and they both move forward in the same direction along a flat road. The idealized graph shows the. They say it's idealized because it should be a smooth curve everywhere, but it's a sort of like a sharp turn instead. Show the variation of velocity against time for both the cyclist and the car from the instant the lights change to green to the instant they are level again. Okay. What's the significance of 0.8 at the beginning of the graph? Okay, so that's their reaction time. That's how quickly it takes them to react. How long does it take from the instant the light change to green for the car to reach the same velocity as a cyclist? Okay, so they're the same velocity at about 6.8 seconds. So your graph will hopefully have a better solid line than mine does there. So about 6.8 seconds. Determine the distance between the cyclist and the car at this time. So to do that, you need to get the area under both graphs. So you need to draw a line down. If you've got the area for the car and the area of the cyclist, and then take one away from the other to figure out the distance in between them. What is the relationship between the average velocity of the cyclist and the average velocity of the car for the time interval covered by the graph? Okay, so all they're after there is how are the two related. So let me show you that with the mark scheme because it's shown quite well in the mark scheme. While we're there, we'll check the other ones. Okay, so reaction time. You can check the other ones yourselves using your ISP document. Okay. So there's the idea of reaction time. There's the idea of 6.8. As I said, there's the idea of figuring out the areas on the graph. So remember, the relationship of the average velocity is the fact that it's taking the same amount of time to reach the same distance. The average velocity must be the same. Okay, that's the idea. So it's taking the same amount of time to reach the same distance. Let's get back to the question. So if you figure out the area under both of these, they'll be identical. Okay, so if you figure out the area under this and the area under that, okay, they're identical. So it's taking the same amount of time to reach the same distance. Okay, therefore the average velocity must be the same. Right, question 5. An athlete runs a 100 meter sprint. The idealized graph shows the athlete's velocity change with time t for a 100 meter sprint. Consider the area under the graph. Calculate the maximum velocity of the athlete. So that's Vmax. Okay. So how are we going to figure out the maximum velocity of this athlete? Well, if it's a 100 meter race, the area of this should be 100 meters. Okay. So I've got the idea of, well, it looks like a U over there. I think they've corrected that when I converted that one piece of software to the other. So it is Vmax, so don't worry. Okay, so in terms of the area under this graph, Vmax is maximum velocity. So we've got a triangle and we've got this big block across. Well, the area of this big block, okay, is going to be Vmax times by, well, it's 2 till 11, so that's 9. Okay, this one over here, well, that's going to be half Vmax times by 2. Okay, so that's the area of this. So if we added these two areas together, that should equal 100 meters. So let's do that. So half Vmax, Vmax times 2, add Vmax times 9. Okay. Can't write max today for some reason. There we go. So half Vmax times by 2, add Vmax times by 9. Well, half times by 2 is just cancels out, that equals 1. Okay, so Vmax is this part over here. Add 9 Vmax. So that equals 10 Vmax. I still can't read Vmax. There we go. So end up with 10 Vmax. So 10 Vmax is going to be equal to 100 meters, because we know the whole area under that graph equals 100 meters. But if 10 Vmax equals 100 meters, then Vmax is going to be 100 meters over 10, which equals 10. This is velocity, so it's going to be 10 meters per second. So the answer to that question is 10 meters per second. Nice question to get. So using the axes below, sketch a graph to show the acceleration of the athlete changes during the race. Mark any significant values on the axes. Okay, so we know that in the first 2 seconds is an acceleration that takes place. Well, if this is 10, and that's in 2 seconds, well, the acceleration must be 10 divided by 2, so that's 5. So the acceleration during the first 2 seconds is 5, and then after that the acceleration is 0 because the velocity is staying the same. So in terms of this graph, I'll just sketch it in the space over here. The acceleration on this axis, time on this axis. So it should be across at 5 meters per second squared, and then it drops down when the time is 2 seconds, and it'll be 0 till the end. Okay, straightforward as that. Let's double check those on the mark scheme. Oops, too far. Question 5. Okay, so 100 meters, so I end up with V being 10 seconds using the trapezium method, which is exactly what we did. The horizontal line parallel to the x-axis, that's exactly what we did. Some indication acceleration becomes 0 seconds, brilliant. And the initial acceleration is Vmax divided by 2, so that's 5, which is what we get. Brilliant. So that's the end of ISP Task 1. Thank you for watching, guys. Please feel free to go back and pause the video to see any of my calculations on the sheet if required. Thank you very much.